All right, good morning, everybody. My name is Carl Humphrey, and Pierce Ferreter and I are going to present to you on what to do with all this water. There is a problem at the university of flooding uh, between the area of Etiwanda and Darby, south of Plummer Street. Right now, there's some parking garages. There's the Sang College Extended Learning and some other facilities. There's also some future construction plans laid out by Envision, the envisioning of CSUN 2035. And we're also going to talk about, we're also going to mention the Institute for Sustainability, and as encouraged by President Harrison, there's a goal of reducing the water usage by 15% at CSUN. So here you can see the flooding on Darby during the rain events. What we propose is that CSUN Envision 2035 has a goal of accommodating the future needs of CSUN. Now, Envision wants to, the key goal for Institutes for Sustainability is to reduce the water by 15%. What we're going to present is a third alternative, and that will actually satisfy both. Here's a 3D rendering of the future of CSUN. You can see up in the left corner, there's some student housing and a future parking structure that hasn't been built yet. So to start this project, we want to start off with, where is this water coming from? In the red area is the catchment, basically the water, where the water falls before it gets into our area that we're studying. And Pierce has also highlighted the area in blue, which is a more current structure. It has a current infrastructure of stuff like those little blue boxes are water catchments. And you don't see very many, they're storm drains. You don't see very many of those on this area that we're studying and where all the problems are. I'm going to pass this to Pierce, and he's going to continue explaining.
Thank you, Carl. So like Carl was saying, on the blue, so these two, the red and blue outlines are the subbasins on campus that are affecting the area we're interested in. And so on the right subbasin, you can see it's there's very well designed. There's a lot of catch basins to catch runoff during storms. And on the left-hand side, where the subbasin that affects the new site, you can see there's only a couple catch basins at the very bottom of the subbasin. And so all that runoff in that entire area doesn't have anywhere to go till it reaches the very bottom of the subbasin. And all these sub areas are different types of land uses that will affect the total runoff. So some of them are all pavement, and that creates a high amount of runoff in that area. Next slide, Carl. And so you can see here on the left-hand side, the calculations we had to do for the runoff analysis to get an idea of what was going on in the site. So we used the rational method. You can see the C values in the column. They give you the idea of what type of surface you're using and how that affects how much runoff there is. And we use that along with the areas and intensity value that we obtained from NOAA. And all those together gave us our flow rates across the area we were interested in. On the right-hand side, you can see a topographic overview of the site. And so from this, we were able to determine that water is flowing southward and a little bit to the west as well. And so you can see how the runoff goes and where it's draining at the bottom of the site. Carl? So once we had a good idea of what was going on in the area, the next step was to see how we could use this stormwater to satisfy the goals Carl was talking about earlier. So what we wanted to do was create a network that would collect the stormwater getting drained across the basin, and then redistribute that stormwater in a way that could be used to irrigate parts of campus, or it could be used to supply the water needs of some of the existing structures, as well as potentially future structures on the site. And so in this table here, you can see a little bit of the analysis we did to determine how much water some of these sites require. To do that, we had to take areas of the buildings and areas that needed to be irrigated, and then we used some resources to determine how much water on average those types of areas consume. And we applied that to our model, and we were able to determine demand values for the future site we're interested in. And so over here, you can see a visual breakdown of what I was just talking about. Oh, next slide, Carl. And so here's the areas I was talking about. So the image on the left is the top of the site we are interested in. The image on the right is the bottom of it. And the areas, the red is for irrigation purposes. The blue outlines are for the structures. And also in the top image, you can see one of the future structures that we also worked into our analysis to provide water needs for CSUN's Envision 2035. Next slide, Carl. And over here is the water network that we designed. So on the left-hand side of each image, you'll see where our network starts. So there's the catch basins that we propose to add, or storm drains. And those are the blue rectangles. Those will collect water earlier on, instead of, as you saw earlier, how it has to go all the way to the bottom of the basin to drain. Now we can catch that water earlier on and store it in the storage tanks, as you see in the blue rectangles. Those storage tanks are buried underground, and they will then be able to distribute water to the network you can see in green. So the network, the green is the pipes, and the yellow circles are the nodes that will distribute water to the various structures, future structures, and areas that need irrigation. And that will all be done through stormwater collected in the tanks. Next slide, Carl. And so to do all this analysis, we used a software called EPANet. EPANet's an open source software provided by the EPA. It's a very intuitive software, and it's great for students to get some introduction to water resources and learn it for free. It's really great for the campus. And so on the right-hand side, you can see the model that we created of the network in EPANet. So this model gives you some information. If you can make it out, some of the pipes on the left-hand side, they're green, and the other ones are blue. That's to distinguish between the difference in pipe diameters. You can see the tanks on the left-hand side, as well as pumps that we had to design into the system, since we wanted to put the tanks underground so they would not disturb the campus environment as much. And this software, once we created this model, we were able to run our analysis and see what types of pipes we need. Carl, next slide. And so this is some of the output analysis that we obtained from EPANet. So you can see there's two different tables here, the analysis for the nodes as well as the analysis for the pipes. So we have the elevations of the different nodes that came into effect for our network. When you have different elevations, that will affect the flow of water. And so that was something that played a big part in how it was distributed. There's the demand values that we discussed earlier, and the head and pressure that resulted in our system that at each node. And also the pipes, we had to input the lengths and diameters, and we got values for the flow within the pipes and the velocity of water in it, as well as the friction factor, which is all important in the final design of our system. Carl?
Yeah, thank you, Pierce. So to summarize the study that we did, originally we were talking about a 15% reduction in the water usage, and Pierce, when you sum up his water use per day in the last slide, it's around 12,972 gallons per day. You get a sum total from the water catchment of 46,000 gallons per day, converting the acres into cubic feet and then into gallons, dividing by 365. Since LA gets, let me back up, since LA gets around 14 inches of rain every year, this converts over the area that the rain falls to around 46,000 gallons per day. Now, the LA River is a concrete lined channel, but in other cities and possibly for the future of LA, that will return to a normal river, for which catching all that rainwater and not letting it go downstream is unethical. However, capturing just 5% of this rainfall and allowing the rest, the 95%, to go on to a river to keep it healthy would fulfill the 15% water usage of the 13,000 gallons a day that this site is experiencing. I want to thank everybody, and we're open for questions.
All right, group 3, what to do with all this water? Great job. We do have a couple of questions. Dr. Dermanjan asks, as stormwater is collected and stored, is it treated?
No, this is outside of the scope of our study. We did not design a water treatment center nor a pumping station. The study was mainly focused on quantity and the design of the water distribution system and the sizing of it, whatnot.
A follow-up question says also, how long will it take to recover the cost of the system versus the water usage?
You know, that's another thing that was outside the scope. Unfortunately, we did not have time to finish the cost analysis. I'm sorry, I can't answer that question.
Okay. At this time, we don't have any other questions. Oh, hold on. The main goal is to, so Dr. Malouf says, the main goal is to alleviate flooding and address water shortages. That was
Right.
Okay. Very good. Group 3, Pierce, Carl, and your faculty advisor, Dr. Malouf, thank you for presenting on what to do with all this water.